Hi everyone, my name is Satish. I'm an engineering manager at Google. I work on software to improve candidates' experience when applying to Google and also make assessing candidates easier and equitable. I also manage the engineering team working on CodeJam. We hope everyone is keeping safe in these times. Today, myself and longtime engineer on CodeJam, Pablo, are going to talk through the replace all problem. Pablo, do you want to introduce yourself?
Thanks, Satish. Hello everybody, I'm Pablo. I've been involved in competitive programming since high school, spending about 8 years competing and then another 8 organizing and writing problems for other contests, before joining the CodeJam team 4.5 years ago. Viewers probably want to hear about the problem though, so let's get to it. Satish, do you want to get us started?
Of course. Replace all problem replicates an ability most text editors have, the ability to replace all occurrences of one character with another in a string. In this case, we cannot just choose our replacements freely. We are given as an input R a list of possible replacements that we can choose from. For example, if we choose to replace T with F in the text CodeJam World Finals, nothing happens because there's no T in the text. However, if we choose to replace O with T, every O in the text is changed into a T. We are asked to do the replacement sequentially, so one replacement is an input to the next. Continuing with our example, we can then choose to replace T with O, taking us back to the original. Now, we can once again replace O with T.
Satish, I see that you use the same replacement multiple times, which is allowed by the statement. However, some other replacements from the list have not been used in the example yet.
That's right, we can use each replacement multiple times, but we have to use each one at least once. In this case, we could finish by replacing C with O, then F with O, and finally S with L. At this point, we have used every possible replacement at least once. So this is a valid procedure.
Was that all?
Not quite. At this point, we can count the number of different characters in the final result, and that's our score. In this example, we got to 12 different characters. Unfortunately, this was not the maximum possible score. A different choice of replacements can actually get us to a text with 13 different characters. Pablo, maybe our viewers can try to solve this case from home before we go into the solution.
Satish, let's brainstorm how to solve this in general. If you are viewing this and want to think about the problem yourself without spoilers, this is a good time to stop the video until you do. I think your example shows some insights. When replacing S with L, we lost some diversity because there were L's already in the text. However, when replacing C with O, the overall diversity stayed the same.
Right, because we had changed O to something else before using it. Maybe that is something that we can generalize to avoid losing diversity, since unfortunately there is no way to gain any.
We can build the whole path like that. Replace B with A, then C with B, then D with C, then E with D, etc. The first replacement may lose us diversity like this, but all the others surely won't.
Nice, Pablo. In addition, if A were not in the starting text, we don't lose anything at all.
Since each path can make us lose diversity, this is starting to sound like a generalized version of the minimum path cover problem. Let's make a graph. We can build a graph where nodes represent characters and edges represent replacements. We are trying to use all replacements, that is, cover every edge with our paths, and we are also allowed to repeat nodes or edges. Those are differences from the usual path cover problem.
Wait, once we use an edge leaving a node, say T, the text is guaranteed not to have any T's, so we could use the opportunity to use all other replacements that replace T.
Cool, Satish. That means that covering each node suffices, since we know we can add any missed edges without altering the result. We can also use this idea to just get any replacement that replaces characters not in the initial text out of the way right at the beginning.
So, we need paths that cover each node that represents a character from the initial text that's also the left side of a replacement. So what now, Pablo?
Well, the path cover problem is NP complete in regular graphs, but can be solved efficiently in acyclic graphs. We could deal with cycles like we did between O and T in the example earlier, by simply going through them without losing additional diversity, since cycles are also paths.
That would let us cover any strongly connected component, since there's always a cycle that goes through them entirely. Can we use the directed acyclic graph of the strongly connected components?
Yes! Using maximum matching, it's possible to solve the minimum path cover problem efficiently in acyclic graphs like that one. In our case, however, some paths cost us one diversity and some are free, as we saw before, so we need to modify the standard algorithm a little. I think we can leave that part of the work to our viewers, since there is no better way to solidify the understanding of an idea than to put it to work.
Well, filling out all the blanks and putting it all together in code is still a lot of hard work. What about people that want more?
They can read our thorough analysis in the problem page, Satish. That has every detail and the additional proof that everything is correct, and a time complexity analysis to see how efficient that is.
Oof, this was a lot of work, Pablo. I can't believe some contestants do all this in a couple of hours.
Well, it does take them a lot of practice to get to that level and maintain it.
Everyone keep practicing then. You can always try any of our problems at any time in practice mode. Make sure to view the full problem analysis on g.co/codejam. Bye everyone.
Bye!